we are looking at exploring, here's a function f on the following, which of the following intervals is f increasing. So the first thing I do, before I even think about how I'm going to do the problem, is I've got to think about what do I know about a function if f is increasing. And we have to think about, this is a calculus problem, right? So how does it relate to calculus? Well, what do you know about the derivative if f is increasing? What has to be true? How do you know if you have a rate? Derivative is a rate that's increasing. It's positive, right? So that's our goal. Our goal is to figure out when is the derivative greater than 0. So I'm going to take the function f of x. I'm going to take its derivative. Which is just 300 minus 3x squared. And we're going to find the critical point. So we're going to set the derivative equal to 0. And then we're going to solve. Now, I don't care how much work you need to show for this. What I'm going to do is just move that negative 3x squared over to the other side. Divide by 3. Take the square root. And we get 2 answers. All right. Now, so this is the work. And remember what these are called. These are called critical points. And those are the spot at which we know for sure the derivative is equal to 0. So I'm going to go ahead and just kind of make a number line here. And then we need to test values. Now, what are we testing values in? We're testing it in the original derivative. Well, you might not even have to test the values here. What type of graph is this? It's a parabola that opens downward. So if I was to draw it, these are the zeros of that parabola. I'm not going to draw this graph in, but that's a really poor example of what that graph looks like. But what does it tell you? It tells you that you've got negative values to the left of 10. You've got positive values between negative 10 and 10. And you've got negative values over there past 10. So what if I get rid of that? There's my sign chart. Now, if you didn't like what I just did there, you could pick a value, plug negative 11 in here. You would see negative 11 squared is positive 121 times negative 3 is going to be greater than 300, so this would be a negative. Plug in 0, you get 300, which is positive. And then plug in positive 11 to check values. But when is f increasing? Anytime the derivative is positive. So we're looking at it from negative 10 to 10. It's been a long time since we've done that. Right? So maybe we're dusting off a bunch of cobwebs. Well, so now the next time you see it, you'll be that much better, right? All right, let's try something like this. This one's a little trickier. Actually, you know what? Let me do one thing. Let me give you a quick little hint that will help this next problem. If I go from negative to positive, what kind of point is present at negative 10? It's a 0, so it's a critical point. So is it a max or a min? Minimum, right? We go from decreasing slopes to increasing. So I know that there's a relative minimum there. And then at positive 10, I go from increasing slopes to decreasing slopes. I know there's a maximum here. So notice how the same work we just did, you could answer the question differently. Right? Is it a max or a min? Well, look at this problem. Here's another function, f of x. What is the absolute maximum value of the function? Now we have to be careful with this one. So I'll tell you that. We'll go 2 minutes on it. little bit of a tricky question. It says, what is the absolute maximum? Notice how it doesn't say where. Where means x values. What means outputs or y values. So, what we need to do is we need to kind of basically do that same approach. If I'm looking for an absolute maximum value, I'm looking for when does the derivative change from positive to negative. Well, that's going back to the derivative. So, I have to find the derivative, which actually ends up being a quotient rule. We haven't done that in a long time, so we don't forget about the quotient rule. You don't have to show all your individual steps. But for the quotient rule, I'm going to take the derivative of the top, which is just derivative of ln is 1 over x, times the original second, minus the original first, times the derivative of the bottom, and the derivative of x is 1, all over the second one squared. Now, the nice thing about this is the first part, 1 over x times x. Remember, that's like x over 1. That just turns into 1. That goes away. And then the natural log of x times 1 is just the natural log of x. So there's my derivative simplified. And then I have to set it equal to 0. Now when I'm solving, we can cross multiply. There's one special note here. Right away, if I look at the derivative here, what value can x not be? What value would give us problems? 0, right? So in my mind, I know that x can't be equal to 0 because it would produce an undefined situation. But if I cross multiply, I get 0 equals 1 times the natural log of x. So I just am going to algebraically solve for that. So if I move the ln over to the other side, just to make that positive, and then I'm going to raise both sides to the power of e, x equals e. Now right away, when I was doing this problem the first time, I'm like, sweet, I like that I have an e because there's e's in my answer. Then I have to check. Right? This one isn't as easy to check, but I need to check to the left and right because if it's a maximum, the derivative should go from increasing to decreasing. I'm going to take the simplified version, and we're going to pick a number somewhere over here less than e. How about, well, we can't pick 0, unfortunately. You pick negative e, about 1. 1's actually really friendly, and it gives me a chance to review one property. So what if I plug 1 in here and here? So I get 1 minus the natural log of 1 over 1 squared. What is the natural log of 1? 0, right? That's something that they're going to somehow test you on. And then this becomes 1 over 1. Well, that becomes positive, right? And then I need to pick another point here, and e is like 2.7, so it doesn't matter. Pick infinity if you want, right? Pick a really big number. I'm going to pick 3 just because it's fun. But notice, the natural log of 3 is going to be bigger than 1. I don't know what it is, and I can't use a calculator. But we know that 1 minus that is going to be a negative answer. And that's all I need to know.
How did we do larger than
E is 2.718. If you did in a calculator e to the first power, it's 2.718, so on, so on. So what does that tell us? Well, that tells us there's a maximum. So we have a maximum at E. But it doesn't tell us what the maximum is. It tells us where it occurs. So what do we need to do now? Let's figure out what it is, right? What is the maximum? Takes the original function. Go back to the original function. We know where it occurs. Now we just have to evaluate. What's the natural log of E? Should be 1. Right? Natural log and E reduce each other out, so you're left with whatever exponent is there. And then 1 over E. So the answer well, we didn't know all of this led us to proving that E was where the maximum occurs, but it didn't tell us what the maximum was. So we knew that it occurs, the maximum occurs at x equals E, but to figure out what the actual maximum is, that's where we plug it back in. So the derivative is what gave us the idea of where it occurs, and then the what is actually plugging it back in. Okay, you might remember this problem. I actually think it might be the same problem. I didn't check, but you had a problem like this on your test a while back. And it's dealing with the integral. And this is a fundamental theorem of calculus one. I think we'll do this one together right away. And then there's one more that involves the same concept that you'll apply. I don't know how comfortable we are remembering this, so I don't want to waste 2 minutes. So what do we have? The graph of a differentiable function f is shown below. H is actually the integral of the function f, which has to be true about h. Well, h is the area underneath the curve of f. That's what this integral means. So they're checking, well, what's bigger? H of 6, h prime of 6, or h double prime, and how do we rank that? So that question is really asking us, if this is what h is, what's the derivative? And we go back to the fundamental theorem of calculus here. So if I take the derivative of both sides, I'm taking the derivative of the integral, and I guarantee you they're going to test you on this at least 3 different ways. What does a derivative and integral do to each other? Cancel each other out, right? So the derivative of an integral go away, and technically all we're doing is plugging this this x into the function. Now, if it was x squared, remember how we had to times by the chain rule? So we have to be careful there, but this makes a connection. Okay, well now, h prime is just the same as f. So if you have the graph of f here, this is also the graph of h prime. And then we need to make a connection to a double prime. Well, if I take the derivative of h prime, that's the same as the derivative of f. Remember what this means. These are the slopes of the graph of x, of f of x. And we have the graph, and we can determine the slopes. So now the question is, how does all that relate back to the point at h of 6? So I'm going to start with h of 6. That's the very first given function. And you're not going to get answers here. What does that mean to you? Area under the curve. this is the area under f of x, or f of t is the area under f. We're going from 0 to 6. What do you know about that area? Negative. The area is negative. So I know that h of 6 is going to be a negative x. Right? Now, I need to find h prime of 6, which is reading the graph. H prime of 6 is just the graph. So if I go over to 6, what is that point? 0. And then h double prime are the slopes. Right? Where did I write that? Right here. H double prime is just the slopes of the graph, and that red slope is positive. So, which one is going to be the largest one? Double prime. So I know it's either this one or this one, because double prime has to be the biggest, and then the 0 is right in the middle, so then we have to have h prime of 6, and the smallest leads me to option. Notice how I wrote those connections down. If it was a free response question, they would need to see all of these connections. How does h and h prime and h double prime all relate back to the graph of f? So you do have to write that. I will say for the multiple choice, you could do this problem in your head if you want and not show any work. And that's the ultimate goal because it saves time. Okay. So now I'd like you guys to try this one. Similar concept, just worded a little differently. The figure right here, so here's the graph of f. If you know that f is the same as the integral from 2 to x of g of x, which of the following could be the graph of g? Let's take a look at this one. So, we have to make that same connection we just had. Here's f. Well, how does f relate to g? If I take the derivative of f, that's going to just bring this x and drop it in there. So, f prime is equal to g. Well, wait a minute. If this is the graph of f, and I need to figure out that f is the area under the curve of g, you have two ways to do it. You could think of, well, here's f, and f prime is equal to g. Well, f prime is the area under the curve. If this is a negative area and a positive area, right? That means my outputs from 2 to x has to go from negative to positive. And these are the graphs of g, right? What are you guys thinking right now? Which ones help you out? How about this? This red line. What do you know about f prime right now? Positive. Notice it's an increasing line. This is linear. F prime is positive, but it's also a constant. The same slope the whole time. So now I'm looking for the graph of g, which is the graph of this slope. So which graph is a positive constant? So notice here's always g is the same thing. It's a constant. It's the same number no matter what. It's positive because it's above the x-axis, and it's never changing. And that's what this slope is. Anywhere on this line, this is a positive slope. It's never changing. It's always the same number. So if you needed to, you could say, oh, well, what if this rise over run What if the slope was positive 2 over 1? And where's this graph? It's always at positive 2. So that's the connection we need to make here. Is that if you know how f and g are related, you can help to make conclusions from that. Okay, so we're going to do a quick review. I got to slide this over. Oh, wrong button. So we kind of talked about this already in some of the problems that came up. What if we ask you to find extreme values, right? Absolute max or min. Well, we have the difference between a relative and a global. And we'll talk about that in a second. But how do we find maxes and mins? Well, what if I'm given just a graph of f? That's really easy, right? What's the max? It's here. What's the min? It's right here. But how does that relate to calculus? That's not calculus. So they're not going to ask you a question like that. They're going to ask you, what if you know the derivative? Well, if I have a maximum, what do we know about the slopes leading up to it? Positive slopes versus negative slopes. So, what would that look like as a graph? Well, notice, everything leading up to it would be positive slopes. It's above the x-axis. Then we have our zero slope right here at our critical point. And then we've got our decreasing point. So, other questions they can ask you. When is f increasing, right? We just saw the warm-up. And what I think is really helpful, drawing a sign chart. Unfortunately, you don't get any credit for that sign chart, but it visually helps us out. Well, what about a minimum? Well, what do we know about the slopes leading up to it? They're decreasing. Then we have a zero slope, and then my slopes are increasing. So, we go from decreasing to zero to increasing. Okay, and again, your sign chart can really help you out. What if I gave you a graph that looks like this? Okay. And you know that this is the graph of the derivative. You should be able to look at that and say, oh, these slopes are below the x-axis and above, so there has to be a minimum. What if it doesn't change? What if I go from positive to positive? There's neither. And that's just that flat spot. Right? So if there isn't a change, you still have a critical point right here. But that point does not tell us anything about the change in the derivative, so it's not a max or a min. Okay. Points of inflection. There we go. So what about points of inflection? Well, remember what that is. That's where concavity changes. And the one thing we have to check is points of inflection occur when the second derivative is zero or does not exist. So remember when we took the first derivative and then we took it again and we set that equal to zero and we looked for another sign chart? It's the same thing. So what about a quick graph? Again, this, if you're ever given the graph of f and they ask for concavity, that's not a calculus problem. Right? That's just understanding the vocab. So what do we know here? That's concave up. Here's concave down. Okay. And then same thing here. Concave down. Concave up. Maybe I'll put CC. But what about the derivatives, right? That's where we got to make the connection. So, can we tell concavity from the derivative, the first derivative? Yeah, technically we can. Let's look at a maximum here. If I have a graph of f, so if there's a maximum on the derivative, and I go from positive slopes to negative slopes, the first derivative is changing from positive to negative, that is going to be concave down. Now think of that. The only way I can have a maximum is if I am concave down. If I'm concave up, I can't have a maximum because points are going up. Same thing here. What if I go from decreasing derivatives to increasing derivatives? If you have a minimum, that's going to be concave up. Minimums will occur when that function is concave up. So, the true connection is if we look at f double prime. If f double prime goes from positive to negative, you know that this part of the graph leading up to it is concave up, because the second derivative is greater than 0, it's positive. And then here, you know the second derivative, let's call it CC, is concave down. Because the second derivative is negative. Right. If it flipped around, oh, by the way, how would I know something about this point? This is just a point of inflection. Because the second derivative is equal to 0 there. And same thing here, we could do concave down to concave up. Here you would have the point of inflection because concavity changes. But here, we don't have a change. We go from positive to positive, so we would call this not a point of inflection. You do have to check for the sign change. All right. So that was a very quick review. I don't know how much we want to talk about this. I like to think of it visually. There was something we called the second derivative test. The second derivative test, when we learned about this, said there has to be a critical point. So if there's a critical point, which remember, what is a critical point? It's when the derivative is equal to 0 or does not exist. So if there's a critical point, what do we know? Let's think about that on a graph. If I tell you there's a critical point, you know the derivative at that point, let's call it C, is equal to 0. Well, what if you know that the second derivative is negative? So if you know that you have the concave down, what type of point has to be right here? Maximum. If you're concave down and you have a critical value, the only thing that's possible is a maximum. What if it was concave up? What point would have to be here then if my second derivative is greater than 0? This point switches from a maximum to a minimum. That's what the second derivative test tells you. So you can make conclusions if you know something about the second derivative. But it all starts with this hypothesis. There has to be a critical point, so you have to know that this point, the derivative is 0. Okay. So we got time for a free response. Unfortunately, I can only make this about this big. Here's the graph of f. And I'd like you guys to try these 4 problems. And we'll give you 15 minutes on this, and then we're going to go over it. So, number 1, find g of 3. What I would do for part A is we just have to plug in 3 into the equation. Now, this is free response, so you got to show the setup. You have to show that right there. And then you have to understand, what does it mean? That's the area under the curve. Well, this is the graph of f, and g is the area underneath this curve from -3 to 2. So you have to find this area right here, which you don't have to show work for that. I ended up doing that, and I got 10. Plus, then you have to find the area of this curve right here, which goes down to 2. So you got to find the area of a 1 by negative 2, which is negative 1. And the overall answer should be positive 9. G of 3 equals positive 9. Okay. That's area under the curve. I'll show you how many points that was worth on the next slide, just so you know. B, on what open interval contained on the entire range from negative, or domain from negative 5 to 4, is the graph of G both increasing and concave up? Well, what I need to do is we're comparing G here. So I need to figure out when is G prime greater than 0, because it's increasing. And then I need to figure out when is G double prime negative. Well, how could we do this? Let's make a connection. If this is G, what is G prime? What is it? F of x. It's the derivative. We're going to take this x and plug it in because the integral and the derivative go away. So now I know that this is the graph of f. So I'm going to use its graph and just think of that as a sign chart. Okay? You don't need to show this sign chart, but this is what I would do. If this is the graph of f, which is also the graph of g prime, when is it 0? It's 0 right here, but notice it goes from positive to positive, and then it goes positive to negative. So I have a critical point at negative 3. I've got a point at 2, and those are both when the derivative is equal to 0. And then my signs go positive, positive, negative. Right? Because we go above the x-axis, and then we shift below right here at 2. So, when is G increasing? Well, G is increasing from negative 5 all the way to 2. So I might say that. Now, you don't technically have to write this part, but G is increasing from negative 5 to 2. And now let's look at G double prime. That's the slopes, right? That's the slopes of this. So G double prime is equal to the slopes of this graph F. Well, look at this. I know I have negative slopes, and then positive and negative. So when does G have positive slopes? Let's look at first, where would the points of inflection be? I have 2 of them, because I've got an undefined and an undefined at negative 3 and 0. And then my slopes go from negative to positive to negative. So we know that g of x is concave down from negative 5 to negative 3 and 0 to 4. Well, I still didn't answer the question, right? The question is, when are they both? So when do they overlap? Well, they go from negative 5 to negative 3. And then I go from 0 all the way to 2. So this is when g of x is both increasing and concave down. Now, if you stop there, you wouldn't get full credit if you had this written down. Because it does say, give a reason for your answer. Well, here's my reason. If you noted somewhere that g is greater than 0, g prime is greater than 0, that's increasing. And if you noted somewhere that g double prime is negative and it's concave down, then this yellow highlighted will get you all the points for this problem. Okay. So the other two are pretty quick, and they actually have the answers worked out on the scoring guide. I just wanted to make a connection to the graph. So let's look at how would they grade the first two answers. Try to make this much bigger. All right. So you got 1 point for the answer. My guess is you'd have to show this setup, because if you just wrote 9, there's no context, right? What is 9? G of 3 is 9. You needed to have some connection of G of 3 with a 9, and I recommend showing that in it. Part B was 2 points. You got 1 point for the answer, so there's your point for -5 to -3 and 0 to 2. And then the reason. And notice what they wrote right here. You had to show somewhere that G prime was connected to the graph F. If you don't write that, then none of this makes sense. But then here's the rest of the connection. Since G prime is equal to F, it's positive and decreasing on these intervals. That's the same thing as what we just said. G prime of X is greater than 0, and G double prime of X is less than 0. So those are equivalent explanations. Let's see, what did number 6 say? I have it written down. It was find H of, I'm going to jump back because I don't remember.
The function is defined by
So H is defined by a function that's related to the G that we know up here. Find H prime of 3. So they're saying find the derivative of this. But here's how I would approach it. I would do the quotient rule. So that's the quotient rule. And this was worth 3 points. Now notice, you got 2 points for just showing the derivative. Notice how the derivative has G prime in it. So it's the derivative of the first times the... Actually, they flipped it around. No, they shouldn't have. G was on top, wasn't it? Okay. So they just wrote it, G prime, so the derivative of the first times the second, minus the first times the derivative of the second. We write it a little different in the order, that's fine. All over the bottom one squared. So if you have this, either one of these, that's 2 points. And then you got 1 more point for plugging in 3 and getting the answer. I'm going to give you a hint on where to stop, because this would be a no calculator problem. You can't stop right here, because we have G prime of 3 and G of 3. Now notice, G prime of 3, we can go and check that on our graph. Right? What is G prime? G prime is the point. So G of 3, if I go over 3, what is the point? It's -2. Right? So we're reading the graph and we know how it's connected. So this answer was -2. And then look at this right here, G of 3. Isn't that the area of the curve? Didn't we already find that? And a lot of times that's designed that way, where one of your answers from part A is used down here. Now if you got part A wrong, but you used it correctly, you could still get full points on this problem, which is kind of nice. So anyways, there you go. Now, here's what I would do. You don't have a calculator. Stop right there. You don't get any extra points for getting to your final answer. And if you make an error in simplifying, then you get one wrong because you don't get the point for the answer. But you can't stop when you still have G prime of 3 and G of 3. You have to evaluate these two pieces, and then once you know what those are, you can stop right here. And we want you to, because that saves you time. Right? Now, what if there was another problem here where we needed this answer? Then you would kind of be forced to go to get to that answer. So just be careful on that. All right, part D. I got to remember what this says. So P is defined by a new function. Find the slope of the tangent line to the graph of P at x equals -1. Wait a minute. What's another word for slope? Derivative. find the derivative of b. And then find its slope at -1. So really, this is asking almost the same thing part C asks. It's a different function, different number, but it's saying find the derivative at -1. And that's the slope of the tangent line. So notice we have an inside-outside function. This is testing the chain rule. Let's look at, this was a 3-point problem as well. You got 2 points for the correct derivative. So notice the derivative. It's the derivative of the outside. Keep the inside. And then multiply by the derivative of that inner part. So 2 times x minus 1. Parentheses have to be there. If you didn't have the parentheses, that's technically wrong. And they wouldn't give you the full point. It might give you 1 out of 2. And then all you do is plug in -1 into each spot for x. Do some simplifying. You couldn't stop here because now you got to read the graph. And that's asking you what is the slope of f at x equals 2. So you go back to the graph and see that its slope is -2 because that's linear. And then your final answer, you could stop right here, -2 times -3. You stop there. So, maybe add up your points right now if you gave yourself a little score here. Remember, this is out of 9. Every free response question is out of 9. And your goal is to average 4 to 5 points. I would hope that this is one of the problems where you're more in the 7, 8, 9 out of 9. Because we know there are other problems that it might be a 1 out of 9. Because they're really challenging and you might just forget some concept. But I hope that this is one of those concepts that is more solidified. And if it's not now, it hopefully will be when we get to the AP test. All right. So I just looked and we had about 10 people submit their work from last week. So you got to remember your goal is to correct 1 multiple choice and 1 free response and submit that from last week. And then we're doing the same thing this week. The only difference this week is the answer keys aren't attached. The answer key is separate. All right? And do as much as you can or as little as you need to, depending on if you're taking the AP test or not. All right? One last thing. Tomorrow would have been our official AP test. Had it been a normal year. So think about where we're at right now. And we get an extra, we're taking on the 24th. So we get an extra 21 days to prepare, which is really great. And I hope your confidence will build more and more this week, as well as next week.
I was confused on how to do corrections because it was already.
So you take a look at your work, and if you got it wrong, you say, you look at the answer that they had, and you just correct it. And then you identify, where did you make a mistake? Was it, you know what, I completely forgot about the chain rule. And they use the chain rule. So I would correct it. And yes, all the answers are worked out for you, but that's so you can carefully check your work. So, all right, that's all I have. Everybody on Zoom, have a great day. If you want to come back in the afternoon, we do have another free response question that we could go through if you want to. So come back at 12:55. Adios. See ya. Oh, sorry, I couldn't hear you in math.
Does that just mean to copy the correct one?
Well, yes, to look at it. Like,
and then we talk about the error.
yeah, and just, you could be like, oh, you know what? I forgot about the quotient rule. Which, if you forget about something like that, it screws the whole problem up.
I